Welcome to the next part about artificial neural networks. Within the previous lectures about ANNs, we got in contact with the theoretical part and some hands-on practices, and are now able to answer questions like: how does an ANN work? Why do we need a bias? What is an activation function? Why do we need it? And what kind of activation functions are there? What is an optimizer? Be more precise, what is the idea behind stochastic gradient descent? How does a neural network learn, including updating weights and backpropagation? And finally, how to build an ANN in Keras. In this chapter, we will see if there are other or better optimizers than stochastic gradient descent. We will deal with dropout layers and see what they are good for, and program several ANNs that will focus on classification problems this time. So let's start with the first question. Are there any other optimizers than stochastic gradient descent? First of all, we saw that stochastic gradient descent works good, especially on the small weather dataset that we used, as it steadily managed to decrease its loss. But it takes its time until SGD converges to a minimum, especially when working with datasets that have millions of measurements. We would like to have an optimizer that quickly finds the loss minimum. Luckily, there are a lot of optimizers out there. This video should illustrate how different optimizers find their way to the minimum. As soon as I start the video, all optimizers start from the cross and try to reach the star as quickly as possible. You see that the optimizers take slightly different paths, and some optimizers eventually converge faster than others. That's because they use different algorithms to adjust the model's weights and biases. Besides the fact that some optimizers might find the loss minimum faster than others, we should try out the different optimizers like RMSprop, Adam, Adograd, etc. for an even more important reason. It might happen that one optimizer gets stuck at a local minimum of the loss function and never reaches the global minimum, while another optimizer that uses a momentum term shoots over that local minimum and keeps on searching for the global loss minimum, just as shown in this illustration. In this lecture, we will not dive into the algorithms behind the different optimizers. For now, just keep in mind that there is a variety of them available, and you should consider testing several of them. The next question we want to tackle is about dropout. What is it and why do we need it? The way neural networks learn, they always try to find the loss minimum for the data they are trained on. Especially large networks tend to overfit, as they have a lot of parameters that can adapt to the training data. This, however, leads to a bad performance on testing data, and the model fails to generalize. One solution can be the dropout. It randomly drops connections between the layers in each iteration during training. This way, the network cannot rely on one specific feature, as it might be non-existent from time to time. Hence, the model needs to generalize. This is a network without dropout, and this with a dropout. As you see, some connections disappeared. In reality, those connections are not cut, but the output values are randomly set to 0. A dropout layer is applied as any other layer in our network. In Keras, we call .add on the model and say that we want a dropout layer. The only argument that we will consider will be the dropout rate, which is the fraction of the input units to drop. We will use dropout in the next hands-on lessons. Those lessons will also answer the last question of this chapter: how to use an ANN for classification problems. So, see you there.